Uh, thanks, thanks for the invitation. Thanks for everyone uh, being here. So what I will present is joint work with Biaoma. He is also a former PhD student of India. Now he's in I forget to put his affiliation. Now he's in Shanghai. So now first to. So for this setting, we will be considering locally compact second countable group. So these can be connected. They can be totally disconnected. They can have a discrete path. With regard to if they are connected or with regard to their connected component, their connected component are well understood by the Hilbert solution of the Hilbert fifth problem. And there is no harm to, if G is connected, there is no harm to see it as a Lie group, up to taking the quotient by a very small normal subgroup. And for this group, there is a unique left invariant Radon measure on G called the Haar measure. And here the uniqueness is with regard to up to rescaling. And first of it was proven by Haar in the case of under the assumption that the group is second countable. And it was generalized to just locally compact Hausdorff space by Andrew Weil and Henri Quentin. And the original hard paper is in German. It is published in Annals of Math, but it is written in German. But nowadays one can have a translation of the paper if one is curious by shorter GPT. So, for example, we can consider Rn with the Löberg measure, and also consider the Lie group where the measure is generated by by a left invariant volume form. Other example of locally compact second countable group are obtained by considering the isometry group of some locally compact separable metric space with the uniform convergence. And well, here the Haar measure is not necessarily explicitly given, but we know it exists. So a subgroup is a lattice if it is discrete and of finite covolume. That is, we can find a subset of G, which is of finite volume, and when we consider its translation under gamma, it will cover the whole group G. If such a subset can be chosen to be compact, then we say that the lattice is co-compact or uniform. Again, example, for instance, if the group G is compact, any subgroup will be of finite covolume, as the volume of the whole group is finite. But the only discrete subgroup are finite subgroup. We have example in, for example, in Rn, lattices are any lattices is isomorphic to Zn, and I forget the n. But you have many ways to embed Zn inside Rn. A more general example, if you consider the group of special linear matrices that are matrices of size n with the determinant equal to 1. And when you consider the integers entries of such matrices, it constitutes lattices inside SL and R. Non-co-compact lattice, it is not co-compact. And more generally, if you consider a group which is defined as being the solution of a set of polynomials where the coefficient of such polynomials are rational, then when you consider the solution with the integers in the entries, then it will constitute a lattice. This is theorem by Borel and Harish Chandra. And generally, these are the type of lattices that are constructed. In the general case, this is the construction for lattices inside a semi-simple Lie. Here, when we say well, here Borel, it is Armand Borel, not Emile Borel. And for those who don't know Harish Chandra, well, first it is one person.
So,
And
I have a question. I mean,
yeah.
And here G is semi-simple, yeah.
Yeah, here we are assuming that group G is semi-simple. Because I'm coming to that. And just with regard to Harish Chandra, in basis it is a physician, and he did his thesis with Paul Dirac, and yeah, here we assume that G is semi-simple because in general the existence of lattices is not ensured, and one necessary condition for the existence of a lattice is the group being unimodular, that there exists a left and right invariant Haar measure, and many examples of such a group which are not unimodular are given by solvable subgroup. So here we assume that the Lie group is semi-simple. Well, first of all, we define what we mean by simple. We say that a group is simple if it does not contain a proper closed connected normal subgroup. So here the group cannot be solvable. And here we have also the algebraic simplicity. When we call an algebraic, say that a group is simple if it does not contain any proper normal subgroup. But in the context of Lie group, we more assume that it is closed inside space. And examples are given by, for example, SL and R. And with regard to SL to R, it is simple as an algebraic group. It does not contain any normal subgroup. And we define, we say that Lie group is semi-simple if it is, let's say, it is a finite product of a simple Lie group up to finite index subgroup. Here we can regard each Lie group as the isometry group of a homogeneous space. So if we consider a lattice inside G and we consider its action on X, we consider the quotient of X over gamma, what we obtain a manifold which is of finite volume, which is modeled on X. Locally, it looks like X. And we will intertwine between in representation inside the G or giving an action on the homogeneous space associated to shear. And yeah, here we define the rank of a group being the maximal dimension of embedded, isometrically embedded flutter inside X. And in general, we have a dichotomy between the rank 1 case and the high rank case. And for instance, all the hyperbolic geometry enters in the realm of rank 1 group. And speaking of rank 1 group, we take a lattice inside PSL2R. You can see PSL2R as the isometry group of a hyperbolic space of dimension 2. The isometry is not preserve the orientation. So when we fix a lattice inside the PSL2R and we make it act on H2, in the quotient what we obtain a surface of an orientable surface of a finite volume. It is closed if well, it will be closed if the gamma is co-compact, and it will be a finite volume if gamma is just a lattice. And here we can see the problem or question conversely. If we begin by a surface, let's say of genus greater than 2, because here the topology imposes a restraint on the geometry that we can put on the surface. If it is of a genus 1, when it is a torus, the structure of the geometry of the constant curvature that we can put on the torus is the flat 1. But from genus equal or higher than 2, each surface can admit a structure, a hyperbolic structure. And for fixing a hyperbolic structure amounts to fix a representation of the fundamental group of S inside PSL2R, and the representation where the image is a lattice. And yeah, and here one can put, say, many hyperbolic structure on the surface, or from one hyperbolic structure one can deform it. So one has many ways to embed the fundamental group of the surface inside PSL2R as a lattice. And also here it is up to conjugation by an element of PSL2R. And this is proper to the dimension 2 case. When we go higher in dimension, here when I speak about the dimension, it is the dimension of the manifold. Here the fundamental group uniquely determine the structure on the manifold. Since that if we have say gamma 1, we have to assume that G1 and G2 are semi-simple Lie group which are different from PSL2R. And if gamma 1 and gamma 2 are isomorphic, then this isomorphism extends to an isomorphism between G1 and G2. And originally, Mosto proved it for compact hyperbolic or closed hyperbolic manifold of dimension bigger or equal 3. And I think before that it was first proven in the case of nilpotent group by Maltsev. And after most of it was generalized to other group, and also not necessarily the closed manifold. And more generally, we have regarding the higher rank lattices, that is lattices in semi-simple Lie group of rank bigger or equal 2. We have the Margulis superrigidity theorem, which says that any homomorphism from gamma inside, say, GL and R, where the image is not inside a compact subgroup, then this homomorphism extend to G. Yeah, here Margulis proved it for higher rank lattices, and it was extended to some rank 1 sample Lie group, like SP N1 and the special octonic or the isometry group of well, forgot the space of the. Well, these are hyperbolic group of these are isometry group of some particular hyperbolic space. And in the case of SPN1, it was extended by correlate. And in the case of this special group by Gromov score. And the technique are here are different. They use more harmonic maps rather than the boundary theory. And the theorem does not hold, well, this superrigidity is stronger than the Mosto rigidity. So PSL2R does not have lattices in PSL2R, has no chance to be to verify this property. And also other rank 1 lattices, for instance, lattices inside SO N1 and SU N1 does not also are not the Margulis superrigidity result. Well, yeah, actually, yeah, just one thing. The Margulis superrigidity result does not hold for the SON1, but in the case of SU N1, I know that with regard to the arithmeticity theorem, we don't know if it holds or not for n bigger or equal to 3. So for that type of n, I'm not sure whether it is settled if the superrigidity result does not hold or not. So yeah, that part just keep it aside.
Lamine, I have a remark.
Yeah.
So, in most of superrigidity, you said that there is previously Maltsev theorem on nilpotent groups, but
I think I already
it's different because Yeah. Okay. The extension. Yeah. Okay. Yeah. You know the extension, not that they are conjugate. Gamma 1 and gamma 2 are conjugate. No. What is this? Okay. You formulate most of like this, that any isomorphism between the lattices extends to the as an automorphism of the group. Yeah.
Yeah.
Yeah. Okay. Yeah. This I think yes. Okay. But not that. Okay.
Yeah. Yeah. Well, for that part, I'm not really sure about the Maltsev theorem, but I know also, for example, for the solvable group, there is almost like rigidity, but here in some cases we don't have an isomorphism, or for example, we have let's say between the homogeneous space, we don't have let's say an isometry, but a diffeomorphism between
because
the two.
Yeah, in the flat case, we have many lattices, yeah? Many,
Yeah.
Zn and many lattices, and they are not isometric, but they are finely isomorphic.
Yeah.
Okay.
Yeah. So now when we are fixing a lattice inside G, here when we say irreducible lattices is in the case of a semi-simple Lie group, when we have say G1 times G2, and we say lattice is irreducible inside G1 times G2 if it is not given as a product of a lattice inside G1 and a lattice inside G2, or formulated in other way, and the projection of gamma inside G1 and G2 is dense. So now assume that assume that we have a representation of gamma inside H. This gives rise to so here gamma act on the homogeneous space associated to H, XH. One can define an action of the whole group G on a bigger space through the process of what we call induction of the action. So here what we consider a fiber bundle over G mod gamma. So here the basis is G mod gamma, where and the fiber are for each point, fiber are the homogeneous space associated to H. Now we have G act on the G mod gamma by a right translation. So we already have an action of G on G mod gamma, but we don't have an action of G on XH. But one can define an action on the fiber bundle over G mod gamma where the fiber has XH. So point element of the bases are mapped through the action of G. And the identification between the fiber is given through the action of gamma on XH with the following element. So here, the mapping is doing through the unique element of in gamma, such that, well, first to define the action, we need to fix a fundamental domain for gamma inside G, Borel fundamental domain. And here, this element gamma is the unique element, such that when we compose it with the G times omega, it will lie inside the fundamental domain. This one, the returning cocycle. So this naturally defines an action of G on, you can see it as either the action of G on the space of a measurable section from G mod gamma into XH, or you can see it as an action of G on the product of XH. And in general, when we have an isometric action, we tend more to consider the following space, because inside this one, we can, for instance, consider the not any Borel section, but for example, L1 integrable section or L2 integrable section. So in some cases, we can consider a subspace where we can undo it with the natural metric, which comes from the metric of XH, and we integrate along G mod gamma. And more generally, if here you have the action of G on G mod gamma is transitive. So and also it preserves the volume of G mod gamma, and so as it is the action is ergodic, and generally in a more general setting, we can, instead of considering G mod gamma, we consider a standard probability space on which G act ergodically by preserving action. And we define a cocycle as being a map from G times omega into H, which verify the cocycle identity. So fixing a cocycle amounts to fix an action of G, gives rise to an action of G on, as we have seen before, an action of G on the space of a section from G mod gamma into the, now if H acts isometrically on some space X, is defined action on the space of a section, or also it can see it inside an action on the product of G mod gamma times X. And yeah, here we say that two cocycle are cohomologous if up to deforming each fibers by an element of H, then we obtain the action of the alpha action is given by the beta action up to rearranging each fiber by such a element. And here, of course, the rearranging does not depend on the element G. It is done once and forward. Now we have the Zimmer cocycle superrigidity, which is a generalization of Margulis superrigidity theorem, which states that any cocycle, which comes from G times omega into H, where G is a higher rank semi-simple Lie group. And any such action of, let's say, G on the space of a section from omega into the symmetric space associated to H is given by an action of G times H. But it's up to rearranging the fiber. The action of G or the identification between the fiber depends only on the element G and not on omega. Yeah, and here the tool for that is first the construction of what they call the boundary map from G mod P into H mod L, where here P is a minimal parabolic subgroup. And see this one as the space of a flag variety of complete flag inside Rn. Well, if G is let's say SL and R, and this space verify some ergodic properties which makes things work, and these are two main property. The first one is amenability of the action, that the action is amenable, and also the action is doubly ergodic. So let's quickly look into these two properties, and after that we will see where they are needed. Well, first of all, example of such boundary, for example, when G is a discrete hyperbolic group or the fundamental group of closed hyperbolic manifold, this boundary can take it to be the Gromov boundary on the way with the Patterson-Sullivan measure. And generally, if G is a semi-simple algebraic group, such a boundary is given by the quotient of G by the minimal parabolic subgroup. And such boundary exists in more general case for any standard Poisson boundary of G is G boundary. So verify these two property. So the first one is amenability of the action and not of the group. So let's first define what does it mean, a group being amenable. So we say that a group is amenable if any continuous action on a compact separable space X has a G invariant measure. And this is a property of a small group because it is not trivial to obtain or to have an invariant measure under some action. But if the group is small, one can expect to have such a G invariant measure. For example, if the group is a finite group, you can consider the measure supported on a finite orbit, and consider the counting measure divided by here. Probability more generally, you have a compact group are amenable. We have also abelian group are amenable by Kakutani. And more generally, solvable group amenable. An extension of amenable group by another amenable group is also amenable. And at a time, it was thought that these are the only example, more or less the only example of amenable group. And but there are many others. But with regard to action, for example, if we consider the action, if we consider the group being SLM-R or, for example, PSL2R, and we consider its action on the circle, there are no invariant probability measure. Yeah, here just with regard to definition of boundary here, the action is not is not measure preserving. It just preserve the measure class of V. That is, it does not map a subset of positive measure into a subset of zero measure. So now I will give this definition, which is not the exact definition given by Zimmer. It is Zimmer who introduced the definition and introduced it for a cocycle. But for now, we can see it. We said that an action is amenable if for any continuous action of G on a compact metrizable space, then there exists a measurable G invariant map from the boundary B into the space of probability measure on X. And if, for instance, if you have a closed subgroup of G, then the action of G on G mod H is amenable if and only if H is amenable. So in particular, when we consider G mod P, here parabolic subgroup here are not solvable, but the minimal parabolic subgroup is solvable. So in particular, it is amenable. Hence, the G action, the action of G on or the right action of G on G mod P is amenable. Now regarding the ergodicity, the property of the boundary. Well, first, the action is ergodic. We say that the action is ergodic if there is no G invariant subset which is not of zero measure and not of total measures. In other way, we can say that if you have a G invariant subset, G invariant measurable subset, so it is either of measure zero or it is of total measure. Now we say that the action is doubly ergodic if the diagonal action and we have another notion of ergodicity, which is called the isometrically ergodic. We say that an action of G on a space is isometrically ergodic if for any separable metric space on which G act by isometries, then any G invariant measurable map is constant. Now, this is a notion which is weaker than the double ergodicity. But in the case where the the action preserve the measure, double ergodicity and metric ergodicity. Well, yeah, so it's the notion is metrically ergodic. So double ergodicity and metric ergodicity coincide when the action of G on B preserve the measure. And here why I am defined why I put the definition of metrically ergodic here, because in what follow we don't only need the double ergodicity of the G action on B, we will need the metric ergodicity of this action, of the action on G on B times B. And for an action which is metrically ergodic, one can for instance, consider the action of PSL2R on S1 times S1. It is metrically ergodic, but it is not doubly ergodic, because the action of PSL2R on is not ergodic, because we have the cross ratio, which is a non-trivial invariant PSL or equivariant PSL2R equivariant map from S1 to the power 4 into R. So metric ergodicity is weaker than double ergodicity. And yeah, with regard to, for example, G mod P, one can consider the example when G is Hassel PR, and G mod P is the space of complete flag in R3. That is the subset of a couple of a line and a plane. And inside the product of G mod P, G mod P, we can consider two complete flags, which are in some sense transverse, in the sense that consider L1 and consider L2, A2, L1 and Q1 enter Q2, L3 gives rise to a basis in R3. Or these three lines are not coplan. This subset is of a total measure inside the product, and the action of SL3R on it is transitive. So now we have an extension of the superrigidity result into more general setting, where the target group is not necessarily a semi-simple Lie group, but is the isometry group of some negatively curved space. And here the source group, we are not necessarily considering irreducible lattices inside a semi-simple Lie group, but we consider irreducible lattices inside locally compact second countable group, which are product. We have at least two factors. So if we consider any action of gamma on, say, cut-zero cube complexes, these are cube complex, so that when endowed with the length metric, they have cut-zero space, they are negatively curved. And these cut-zero cube complexes were studied in the aim of understanding fundamental group of hyperbolic 3 manifold. Because if you have a group that is hyperbolic and which are geometrically on cut-zero cube complex, then the stabilizer of a hyperplane inside the group are nicely embedded inside the group edge. Anyway, so with regard to lattices inside irreducible lattices inside G1 times G2, any action which is, say, non-elementary, that is, it does not have a finite orbit, it is minimal. That it doesn't fix a convex. There is no closed convex invariant cut-zero cube complex inside the space. And they Chatterjee-Fernand showed that any such action extend to the whole group G1 times G2. And in particular, they showed, for example, if G1 and G2 are connected, then any such action has a fixed point. Any such action of gamma has a fixed point. And in somewhat different setting, the same result holds for action of such lattices on the isometric action on the cut-zero spaces, or Guzman negatively curved space. For cut-zero space, it was done by Mono, and in the Guzman negatively curved space, it was done by Gerlander, Carlson, Margulis. But under the assumption that gamma is square integrable inside G1 times G2. And this condition is needed to show that the action of the induction of action of G1 times G2 on the space of section from G mod omega into X is well defined on the space of G mod gamma of L2 integrable section from G mod gamma into X. And if the space is cut-zero, this one is naturally endowed with the canonical metric is endowed this space with the cut-zero metric. And the techniques are different. For Mono, he used a splitting result, as he has an action of G1 times G2 on this cut-zero space, which is really big. It is infinite dimensional, but having many elements which commute constraints the space or impose the existence of G invariant subspace, which split as product of Z1 times Z2, where G1 acts on Z1 and G2 acts on Z2. With regard to Gerlander, Carlson, Margulis, they did the same thing, but the splitting result they obtained it by harmonic tools. And this subspace is this subset of such function which are harmonic with regard to a specific energy function, which depends either on G1 or G2. with regard to isometric action on finite rank median space, it was shown by Fioravanti, and also the same this result hold regarding the fixed point property when the group G is, for instance, connected. But also under the assumption that that gamma is a square integral. But with regard to Chatterjee-Fenoz-Yorzi result, it does not assume that the lattice is a square integral. But they use the boundary theory, which is stronger in a sense. With regard to cocycle superrigidity, if for the same group G, where G is a product of G1 times G2, any non-elementary cocycle having image inside the isometry group of a negatively curved space. So in their setting, it is either locally compact cat-1 space or proper hyperbolic of finitely generated hyperbolic group or a locally finite tree. And here we say that it is non-elementary if it is not, the cocycle is not cohomologous to a cocycle taking image inside the stabilizer of a point or a subset. So for the first part, we state our result with the Biauma, and the result we showed for the same kind of source group, reducible lattices inside the product of locally compact second countable group, and the target space is the isometry group of a separable median space of finite rank. And the results state that such cocycles are cohomologous to a homo. There exists a median subspace inside X, which is invariant by the cocycle. In fact, it is invariant by the whole isometry group of X. And when we consider the restriction on such a subspace, the cocycle is cohomologous to a cocycle given by an action of G on this median subspace. Yeah, so I will stop here for the first part.